everyone, it is with a great pleasure and enthusiasm that I stand before you today. In the next few moments, I'm thrilled to share insights on skin lesion classification based on vision transformer, a topic that merges cutting-edge technology with critical healthcare needs. We will explore how innovative vision transformers model is revolutionizing the classification of skin lesions, offering a promising avenue to enhance diagnostic accuracy and streamline patient care. So before we delve into this groundbreaking intersection of artificial intelligence and dermatology, let's have a look on the followed outline. Of course, we will start with an introduction and objectives. Then we will see some related work. We will have an overview of the proposed architecture, which is vision transformer. Then we will see datasets used and the evaluation metrics, the implementation and results obtained, and we will end with a... So let's start. Skin cancer is a global health issue, with melanoma being the most lethal form. The International Skin Imaging Collaboration (ESIC) datasets, one of the largest publicly available skin lesion datasets, is pivotal in advancing research and AI solutions in this field. This research focuses on using Vision Transformer, a state-of-the-art deep learning model for skin lesion classification. The accurate detection of skin lesions is important for early diagnosis and treatment of various skin conditions, including skin cancer. And traditional approach relied on handicraft features and shallow learning algorithms, but recent advancements in deep learning and computer vision offer new possibilities. Let's discover it together. Before to discover these new possibilities, let's have an overview of the objectives that we have to achieve in this work. So the first or the main objective is to develop a classification model using vision transformer architecture. This, of course, involves training the model on datasets of skin lesion images, ensuring it can effectively differentiate between melanoma and non-melanoma. And then we have to evaluate the model performance, of course, assess the performance of the vision transformer model on relevant datasets, comparing its accuracy, precision, recall, and other evaluation metrics against existing state-of-the-art methods. This evaluation will help determine the effectiveness and efficiency of the developed model in classification or in classifying, of course, skin lesions. Well, in general, this study aims to explore the potential of vision transformer in skin lesion classification by leveraging self-attention and hierarchical representations. Vision transformer offers advantages over traditional methods in capturing complex patterns and contextual dependencies with skin lesion images. As I mentioned before, the early detection is crucial in treating skin lesions, particularly for conditions like melanoma. Delayed or incorrect diagnosis can lead to disease progression, of course, and limited treatment options. For this reason, deep learning models, particularly convolutional neural networks or CNNs, they have shown remarkable performance in this field, and however, they have a limitation in capturing global context and long-range dependencies in images, which affect their ability to understand complex relationships between different parts of an image. This is where vision transformers come into play. So this is the architecture of the proposed model, which is ViT or vision transformer. ViTs represent a paradigm shift in image analysis by leveraging the transformer architecture originally developed for natural language processing tasks. The image, as you can see in the picture or in the image is divided into a small fixed size patches. Each patch is then linearly projected to a lower dimensional vector called patch embedding. These patch embeddings are treated as words or tokens and become the input of the transformer model. After the patch embeddings have been processed by multiple transformer layers, the final layer's output processed to a classification head, which is multi-layer perceptron. The classification head is responsible for taking the encoded information from the transformer and mapping it to the desired output for the specific task at hand. So the ViT combines the power of transformers and self-attention to yield superior results. Here we go. This is the arc of the transformer. Transformers, known for their ability to capture global dependencies and learn meaningful representations from sequential data, and they have proven highly effective in language understanding, and our architecture harness this power and adapt it to the realm of computer vision. However, this happens by replacing the convolutional layers of CNNs with self-attention mechanism. ViT excel at capturing both local and long-range dependencies within an image or within the images, and this is the goal. As mentioned in the architecture, the transformer consists of two main parts, the encoder and the decoder. And what's concerned as encoder is this part surrounded with the red line. So this encoder consists of a series of identical layers, and each layer consists of two parts. The first part is a multi-head self-attention mechanism, while the second part is a simple fully connected feed-forward network that operates on each position individually. They incorporate a residual connection around each of these two parts, followed by a layer normalization, which means that the output of each part is normalized by adding it to the original input. Now, let's discover the mechanism of self-attention. Self-attention is a mechanism that allows the model to attend to different parts of the input and learn the relationships between them. Yes, and this is happened, of course, by using the scale dot product attention. So self-attention involves three key components: queries, keys, and values. For each token in the sequence, self-attention calculates its representation by attending to other tokens in sequence based on their relevance or importance. Multi-head attention, of course, it consists of several attention layers running in parallel. Now that we have discovered the architecture and the key components of the proposed architecture, which is ViT, let's discover the datasets used in this work and also the evaluation metrics. In this work, we have used two datasets, PH2 and ESIC datasets, and as you can see, each dataset contains a number of images, melanoma, of course, and non-melanoma, and the images, of course, they are in RGB. Now, concerning the examples, those are some examples obtained from both datasets. Of course, examples of melanoma and non-melanoma skin cancer. Let's move now to the metrics or the evaluation metrics used. As you can see, there is recall, specificity, precision, and accuracy. Now let's discover the main steps of the implementation. Well, As first step, we have data pre-processing. The image were resized to a standardized dimension and converted into NumPy arrays. We have data splitting. The dataset was split into training and testing sets using the train set split function from scikit-learn. This ensured that the model's performance could be evaluated on unseen data. We have also data augmentation. Various data augmentation techniques were applied to the training images. These techniques include normalization, resizing, random flipping, and rotation. And then the creation of the vision transformer model, and of course it has been developed from scratch. So our architecture includes patch extraction, encoding, multiple transformer layers, layer normalization, flattening, dropout, multi-layer perceptron, and classification. It's effectively utilized self-attention mechanism to capture complex spatial relationships in images. And without forgetting Adam Optimizer, it has been used to optimize the parameters of the model during the training process. The last step, of course, training. And here I mentioned some hyperparameters used, like learning rate, batch size, the number of epochs, the size of the image, and the size of the batch also. Okay, now let's go to the most exciting part, which is the result obtained in this work. Before to mention the results, I have just to mention that we have worked on two different data sets, as I mentioned before, and we have worked with 3 models. We've applied the self-attention mechanism, and then we've applied the transformer and then the vision transformer model on the 3 data sets, and we've got results from different models on both data sets. Let's start by the PH2 data sets, especially self-attention. So the results obtained using the self-attention, as you can see, those are the evaluation metrics, and the accuracy were 95%. This is the accuracy obtained using the transformer, 92.5%. This is the accuracy obtained using our architecture. It's 95, like the self-attention. Now let's move to the second data sets, which is ESEC. Well, for the results obtained using self-attention, the accuracy was 83.14%. And those are the evaluation metric. Also, about the transformer, the result or the accuracy was 84.53%. For the architecture proposed, or VIT, 90.05%. Now we have seen the results. Let's discover a comparison, as we said, against other existed models. So in this table, we compare the performance of VIT architecture with that of the other deep learning models, like AlexNet, VGGNet, GoogleNet, ResNet, and as you can see, VIT shown the most interesting results or accuracy. Concerning, or in summary, our research explains the potential of vision transformer model in the realm of image recognition and classification, particularly in the context of skin lesion analysis. By optimizing hyperparameters and harnessing self-attention mechanism, we achieved promising outcomes in accurately classifying skin lesion images. The implications for healthcare and the broader field of computer vision are significant. Further research and exploration of ViT model hold promising prospects for advancing image analysis and classification techniques across various domains. Thank you for your attention.